Hello. In this lecture, I will tell you a little bit about cyclic alkanes and how stable they are from 3-membered rings, 4-membered rings, 5-membered rings, and on up from there. Turns out there's considerable differences in stability for different sizes of rings, and that has to do with bond angles and has to do with eclipsing and staggered, and ultimately gives rise to actual 3D shapes that these molecules take on. So, before we can do that, though, we need to talk a little bit about what does stability mean anyway. Well, basically, it's a code word for how much energy does a molecule have. If a molecule has lots of energy, then it is not very stable. And if it doesn't have very much energy, then it is pretty stable. Because if it doesn't have very much energy, it basically just sits there, doesn't really want to do anything. But if it has lots of energy, then it wants to do all sorts of stuff. Reactions with other materials and changes within its own structure and that sort of thing to try to become more stable. So the more energy it has, the less stable it is, and so on. Now we talk about energy in terms of heat of formation. You remember from general chemistry that any molecule will have a heat of formation, which is, if you remember, basically how much energy does it have compared to the elements that it's made up of. And so since all substances are made up of elements, we can compare the stability of one substance to the stability of another by how different are they from their elements. So if one has more energy compared to its elements than another one has, then what we say is that it's less stable. Now we do this in terms of grams rather than moles because just naturally if a substance has more carbons, for example, then it will automatically have more energy. It doesn't necessarily mean that it's less stable. What we really need to do is look at stability per gram rather than stability per mole, because big molecules, of course, will have more grams, and what we want to do is look at it per gram. So what I've done here is listed, I looked up in the CRC handbook, what is the heat of formation of several different cycloalkanes from cyclopropane, cyclobutane, cyclopentane, cyclohexane, cycloheptane, and cyclooctane, 3 through 8 members in the ring. And I listed it both in terms of kilojoules per mole, but more interesting in terms of kilojoules per gram. This is really going to tell us how much energy does the molecule have, not because of the number of carbons it has, but because of the way the carbons are arranged with respect to each other. And notice, if you will, that cyclopropane has a heat of formation of 1.26. Now you may remember from general chemistry that most heats of formation are negative. This is a positive number, meaning it's bigger than most other substances, which means that it has more energy than most other substances, which means that it's less stable than most other substances. So cyclopropane, as we will see, is full of energy and therefore not very stable at all. Cyclobutane has less energy, 0.5 is less than 1.26, so therefore it's more stable than cyclopropane, but it's still a positive number, which means cyclobutane still has quite a lot of energy compared to other substances. When we get cyclopentane, we see that it's now negative, which means it's even less energy than cyclobutane. Obviously, -1 is a smaller number than 0.5. And so as we go from 3 to 4 to 5, they're getting less and less energy. Cyclohexane, considerably less energy. Of these four, this is by far the most stable because it has less energy than this by about 1, roughly, kilojoule per gram. Less energy than this by about 2.5, roughly, kilojoules per gram, and less than this by roughly 3/3 kilojoules per gram. When we get cycloheptane, we see that it goes back up again because this now is a bigger number than this. So cycloheptane has more energy and therefore is less stable than cyclohexane, and cyclooctane even less energy. So basically, starts out high, goes down, down, down. This is the lowest energy of them, and then it starts to go up again with cycloheptane and cyclooctane. What we want to do is see if we can understand why. So let's start with cyclopropane, and I've made a model of it. It's a 3-carbon ring with 2 hydrogens on each, as indicated by this structure right here. This is a perfect triangle, and you'll notice that mathematically it should be a 60-degree angle in there. So this has to be a 60-degree angle because it has to be a perfect triangle. Now, what do you think about how happy a carbon is if it's got 4 groups attached to it, therefore tetrahedral, and yet it's being forced to be 60 degrees? That's a really bad thing. 60 degrees instead of 109.5 means that there's a lot of what we call angle strain in there. Furthermore, if you look down one of these bonds, notice that the hydrogens are lined up directly, and that's true if you look down any one of these carbon bonds, they line up directly. We call that what? We call it eclipsed. And what do we know about eclipsed versus staggered? Less stable. And that idea, where the hydrogens have to be eclipsed, is called torsional strain. So fluoryl cyclopropane has a terrible amount of bond angle strain and also torsional strain because all the hydrogens are eclipsed. In some molecules, as we will see, they can twist some of the bonds and make the hydrogens that are not quite as eclipsed, but fluoryl cyclopropane can't do that because 3 points constitutes a plane, and there's no way it can get out of a plane because no matter how it does it, it's going to be in a plane, which means the hydrogens are always going to be eclipsed. Now, let's go to cyclobutane. Cyclobutane, oh, by the way, you may have noticed in my cyclopropane molecule, I had to use springs for these bonds instead of sticks, and that's because sticks don't bend. And since the angles in these balls are cut to be 109.5, they can't be 90 degrees or the sticks will break. So we have to use springs instead. And I did the same thing for cyclobutane because what is the angle in a square? Mathematically, according to geometry, what does that angle have to be? It has to be 90 degrees. What does it want to be if it's got 4 bonds to it? 109.5. So again, not what it's supposed to be. Not nearly as bad as 60 degrees was for cyclopropane, but still not perfect. And so we might guess, just based on those angles, that it's still pretty high in energy, as we saw that it was, but not as high as cyclopropane is, and that is correct. Furthermore, you'll notice that like cyclopropane, cyclobutane, if it's flat, and that's the key, if it's flat, the carbons line up, the hydrogens line up, all 4 bonds are eclipsed, and therefore it has considerable amount of torsional strain as well as angle strain. However, cyclobutane can do something that cyclopropane can't, and that is twist. So what we can do is actually rotate around all 4 carbon-carbon bonds at the same time and twist it like this. And what you'll notice is if you do that, you can make the hydrogens so that they're somewhat skewed off a little bit, like a little bit staggered, not quite perfectly staggered, but it relieves some of that torsional strain so the hydrogens aren't quite as eclipsed. However, to do that, you have to actually force the angles in the ring to be smaller than 90 degrees. That's going the wrong way. They want to be bigger than 90 degrees. So in essence, what cyclobutane has to do is sacrifice some angle strain in order to get rid of some of the torsional strain. And it does do that a little bit. So actually the conformation of cyclobutane is slightly puckered, not flat. And we call that conformation, we call it butterfly conformation. Then we'll see the butterfly flying. So cyclobutane not nearly as bad as cyclopropane because the angle isn't nearly as bad as 60 degrees and because it can get out of the eclipsed form a little bit. What about cyclopentane? Well, now we have a molecule that I can use sticks on because in fact, in a perfect pentagon, and you can calculate this yourself or you can look it up, in a perfect pentagon the angle should be 108 degrees. How does that compare to 109.5 from what a tetrahedral carbon wants to be? Pretty darn good. In fact, the difference is insignificant. So really the angle strain for cyclopentane, as long as it's flat, is essentially 0, has no angle strain. So that's a good thing. So we might expect that cyclopentane would be pretty stable. However, if we look down the bonds, again, we notice everything is eclipsed. And so that's bad. It still has considerable amount of torsional strain. Can it do anything like cyclobutane does, where it twists a little bit and relieves some of the torsional strain? And the answer is yes, a little bit. I can actually move one of these carbons slightly higher than the other ones, and that then means that the bonds around this part of the molecule are not quite eclipsed. They're not staggered, but they're a little bit less, they're a little bit skewed off from what they would be if they were eclipsed. So that provides a little bit of relief from the torsional strain. However, to do that, you have to actually decrease the size of the angle a little bit, so it becomes even smaller than 108 degrees, not significantly, but enough that it has to sacrifice a little bit of that bond stability in order to relieve some of the torsional strain. So this kind of conformation, where one carbon is a little bit higher and the other 4 are in a plane like this, it's called an envelope conformation, because this part of the molecule reminds some people of the flat part of an envelope. This part is kind of like a flap of the envelope. So that's cyclopentane, again, considerably more stable than cyclobutane, and as we saw when we looked at the numbers, it was considerably lower in energy. Now, we get the fun one. This is cyclopropane. cyclohexane. And cyclohexane, according to if it were flat and if it were a perfect hexagon, the angle would be 120 degrees. How does that compare to what a tetrahedral carbon wants to be, 109.5? The answer is it's quite a bit off. So we might expect that cyclohexane would have a fair amount of angle strain. And furthermore, all the hydrogens, again, if it's flat, are eclipsed. So these hydrogens are eclipsed, and 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 so on. So it has, again, if it's flat, and that's the key, if it were flat, it would have considerable torsional strain and considerable angle strain, and we might expect it to be less stable than cyclopentane. In fact, as we saw when we looked at the numbers, it's the most stable. It's considerably more stable than cyclopentane. So why is that? And the answer is because it can twist its bonds and pucker up, just like cyclopropane and cyclobutane can do. But when it does, all 6 bonds rotate into what we call a chair conformation. So notice that these 6 carbons, I don't know if it looks like a chair to you or not. You might be able to sort of turn it in space a little bit and make it look like a chair, but that's called the chair conformation. And what you'll notice about it is, in fact, notice that I use sticks in this model because the angle turns out to be 109.5. So it's perfect in terms of its angle. It has no angle strain whatsoever. And furthermore, if you look down the bonds, what do you notice about the hydrogens here? Perfectly staggered. If we look down this bond, perfectly staggered. If we look down this bond, perfectly staggered. In fact, all the hydrogens are staggered with each other. So this hydrogen dihedral angle is exactly between these hydrogens, and this one is exactly between these hydrogens, and so on. So all of the hydrogens are staggered, and all of the angles are 109.5. So it's a perfect molecule. Cyclohexane is one of my favorite molecules for that reason. It's what you might call nature's perfect molecule. If we move on to cycloheptane, I didn't make a model of this, but you will get the idea. If you look at a regular heptagon, you can calculate that the angle should be 128 degrees. Again, pretty far off from the 109.5 that it wants to be. And furthermore, like all the rest of them, if it's flat, all the hydrogens are eclipsed. So it has a lot of torsional strain and a lot of angle strain. But like cyclohexane, because there are 7 carbons here, you can twist some of the bonds and into a conformation that looks kind of like this. And in so doing, the angles become much closer to what they should be, 109.5. Although these 2 angles are not quite 109.5. The rest of them are pretty close. But furthermore, all of these hydrogens are staggered with each other, so that's a good thing. However, these hydrogens over here are still eclipsed, and so that's a bad thing. So cycloheptane, not quite as stable as cyclohexane, and so that's why its energy went back up again. Remember, the energy went down to cyclohexane and then back up again to cycloheptane. And as you can imagine, it's going to be the same sort of thing for cyclooctane and cyclononane and cyclodecane and so on. They will go up a little bit, little bit, little bit. But the lowest is cyclohexane, even though we might expect cyclopentane to be the lowest. And let me give you a little history here, just a little side note. There was a fellow German chemist named Bayer. If you change the pronunciation of his name a little bit, you get Bayer, and he did in fact start Bayer aspirin. But he was a chemist, and he was interested in different sizes of rings, and what he predicted was that cyclopentane should be the most stable based on the angles. The angles are 108 in a pentagon, and not that in a perfect hexagon. But he was wrong, because it turns out cyclohexane was the most stable, and that's because it's puckered. It's not flat. Therefore, the angles aren't 120 degrees. They are 109.5, which is what they're supposed to be. And furthermore, again, no eclipsing. Everything is staggered. And that's the end of that lecture. Thank you for your attention.